So this example will show you how to create a regression equation for some data. In this case, we have the average temperature in degrees Celsius versus the gas consumed in cubic feet for a house that has just installed insulation, and this was collected for random winter days. So the first thing to realize that it is in fact a regression analysis, and the way I know it's a regression analysis is that I happen to have two different types of variables. I have a temperature and gas consumed. So usually when we have two different types of variables like this, we are going to be doing a regression analysis. So our first thing we have to figure out is what is in fact our predictor variable and what is in fact our response variable. The predictor variable is the variable we use to predict the other variable. It's usually called the independent variable. We usually use X for that. The response variable is gas consumed, and we usually call that Y. In this case, it makes more sense for temperature to predict how much gas you're going to consume than the other way around. So I went ahead and decided that X would be average temperature and Y would be gas consumed. So now we can actually go to find the regression equation between the average temperature and gas consumed. So I'm using R to do this example. There are other softwares out there that you can use. The main thing to realize is the output is what is of importance. So looking at this, we can see what our outputs are, and that's really what you want to look at. So in R, we would type the data in. I called temperature temp. I called gas consumed gas. You can call them anything you want. It really doesn't matter. In R, I would call this linear model lm.out. This is just naming the model so I can call it later and use it later. And the command for creating a regression equation in R is to do lm and then gas. This is a tilde, which is the key that's kind of next to the number 1 on your keyboard, and it's a shift on that, so it's called a tilde. And so you do the dependent variable or the response variable tilde the independent variable or the predictor variable. So that will run it. Nothing will happen when you do that in R, so the next command you would do is the linear model out here, and that would actually mean that it will show you what it created when it did this command. So if we move down, it will give you this as your output. And again, a lot of other softwares have this kind of output, so that's more of what you're looking at. The regression equation, general regression equation, is y hat is equal to a plus bx, where a is your y-intercept and b is your slope. So looking at here, it actually gives you the coefficients. This one, it actually calls the intercept, so that's your y-intercept. So y hat is equal to 4.571. And then your temperature value here, that's actually your slope. So this number here is your slope. It is negative, so we'll do negative 0.223x. So at this point, I probably would rewrite this as 4.571 minus 0.223x. The reason I use the y hat is because this is from sample data, so that allows me to know that this is a sample information. This is actually an estimate, therefore, for the true regression equation that's out there. This is just what we came up with. A different random sample will create a different estimate. So now that we have a regression equation, we may want to look at a scatter plot and see how well the regression equation fits to the scatter plot. So let's go ahead and do that. Let's graph the regression equation on the scatter plot. In R, you would plot first your scatter plot. So the plot temp, gas means that it'll put temperature on the x-axis, gas on the y-axis. And I went ahead and labeled outside temperature versus gas consumed as my title. Technically, I should have labeled the x-axis and y-axis a little bit better so that I'd have the degrees Celsius and the cubic feet, but at least I have some labels on here. And then this AB line, that is allowing it to actually put a line on your plot. Don't close the plot window after you create it. So you create the plot window and then you do this AB line back in the command lines. And then linear MLLM.out is what we called our linear model. So what this is saying is we want to plot the linear model on here. And just to make it stand out a little bit better, I called it red. So that's that red line here. Noticing that most of these dots seem to fall along that line. We have a few dots like this one that's kind of out there, and these that are kind of far away from the regression line. But otherwise, that regression line seems to fit fairly nicely to the data. You could find the residuals at this point by figuring out how far away each of these values are from the line and get a concept of your residuals. So now that we know that our line fits okay, and we know that we know what the line is, we can now use that line. So let's go ahead and use the line. We'll use the regression equation to find gas consumed when the temperature is, let's say, 3.5 degrees Celsius. So remember, our y equation is y hat is equal to 4.571 minus 0.223x. In this case, since x is my temperature, they are telling me that x is equal to 3.5. So all I gotta do is stick 3.5 into my equation. And then go ahead and find out what that equals. And it turns out that that equals 3.8 cubic feet. Don't forget the units. So I should put the units on x too. So that tells me that when the temperature outside is 3.5 degrees Celsius, which is above freezing, I'm going to use 3.8 cubic feet of gas. If I go back and look at my data for just a second, I will notice that I don't actually have a 3.8 as one of my x values. I've got a 3.9, I've got a 3.1, I'm close to it, but I don't actually have a 3.8. I noticed that when I have a 3.9, my value was 3.9 as gas consumed, and I just came up with when 3.8, we actually had 3.8 cubic feet of gas used. So it seems like it fits in quite nicely with our data. And that's kind of a nice feeling. So this is actually what is known as interpolation, because I'm estimating data from an x value that's inside my data. So when I had my 3.5, I'm sorry, I think I called that 3.8. It was 3.5, but it's still the same idea. It roughly fits my data. All right, so let's do another one. Use the regression equation to find the gas consumed when the temperature is negative 5 degrees Celsius. So again, in this case, my x is equal to negative 5 degrees C. So y hat would equal 4.571 minus 0.223 times negative 5. And that comes out to 5.7 cubic feet. So if I go back and look at my data again to see how well that fits it, I notice I don't have a negative 5. The lowest value I have is actually a negative 0.7 for my temperature, so negative 5 degrees Celsius is pretty far away from my data, and 5.7 doesn't look like it's too far off. I don't know how great it actually is, but it's not too far off. And the reason that it's not perfect and how great it might be is because this is what is known as extrapolation, when we're measuring or estimating a value for y from an x value that's not within the original range of the data. So we can see we're not really sure how far off it is, but we're not perfect with that value. Let's do one more. So let's say we want to find the regression equation, or use the regression equation to find the gas consumed when the temperature is 25 degrees C. So then y hat is equal to 4.571 minus 0.223 times 25, and that ends up with a value of negative 1.0 cubic feet. Well, if I look back at my data, I'm going to see 25 was not one of my original data values. In fact, it's nowhere close to any of my original data. And a value of negative 1 cubic feet doesn't make a whole lot of sense for gas consumed. You can't use a negative 1. That would mean that you're actually giving gas back to the company, basically. And that doesn't really make any sense to do. And so we wonder why this estimate is pretty far off from what it should be. And again, because this value is not within the range, this is extrapolation. And extrapolation is kind of dangerous sometimes because you don't really know that your linear model actually is still accurate. So your regression equation may not be accurate anymore, way far away from the original data, which is why extrapolation is not a good idea. In reality, if you think about this, 25 degrees Celsius is a fairly warm day, and so you wouldn't be using any gas to heat your house. So that's a regression analysis.